very pleased that we have Dr. Annie Kritcher here from Lawrence Livermore National Laboratory. Annie is the lead designer for these small pellets that are exploded in a hydrogen bomb-like fashion at Livermore. She's got her undergraduate degree at the University of Michigan. Her graduate degree, PhD, is from here in nuclear engineering. Annie is a fellow of the American Physical Society. She's on the leadership team for the National Ignition Facility at Livermore. If you saw their press conference for the famous shot that she's talking about, the shot heard around the world, you'll see that she did a great job on TV, being interviewed in Washington, D.C. One thing to say here, which is a quiz for the audience. What does Annie have in common with Sam Altman, Joe Biden, Michael Jordan, and Lauren Powell Jobs? And 96 other people. That's a big hint. Annie was chosen last week as one of Time 100's most influential people in the United States for the year 2023. And the reason for that is what she's going to be telling you about now, is the challenges and promises of inertial fusion. So Annie, let's welcome Annie Kritcher.
All right, can everyone hear me? Great. Thank you all for coming today. I'm really excited to tell you about how we achieve target gain greater than 1 in fusion experiments at the National Ignition Facility. So on December 5th, 2022, a significant advance in the ICF research area was made. We did an experiment that showed that there was nothing fundamentally limiting achieving fusion energy gain in a controlled laboratory setting. This is a plot of yield fusion energy produced as a function of calendar year. And each bar on here is a DT experiment or shot that we did at the National Ignition Facility to try to produce this fusion energy. And even though you can't quite see it, there are points down here. This is the beginning of NIF, but they're so low now compared to what we're doing in the last several years, it's sort of off the chart. So back in 2021, we achieved ignition by Lawson criterion. I'll talk a little bit about that. And then most recently, we achieved target gain of 1.5 roughly, which is that the energy from fusion out is about 1.5 times the energy of the laser into the target. This shot reached over 30 quadrillion watts of power, but for 90 trillionths of a second, so very short-lived. We burned up about 4% of the DT fusion fuel. Pressures in this hot plasma that generated the fusion were more than 2 times the center of the sun, and temperatures more than 5 times the center of the sun. And now, because of this shot, the NIF now meets all the definitions for ignition and satisfies its namesake of the National Ignition Facility. All right, yes, and still a very long way to go to get fusion energy on the grid. This is a research facility and a proof of principle experiment, and there's quite a bit of ways to go. I'll talk about that at the end as well. So many thanks to all of the people that have contributed to the NIF and this result over many decades. We have partners at the other laboratories, at universities, at companies. And of course, this has been first proposed in 1960, so a long time coming. So thanks to the many people that worked on that and some people in this room as well. So we've been waiting for this experiment since the 1972 Nuckolls paper, actually before that, when he first proposed inertial fusion with lasers. And he proposed this so that we could make these microfusion explosions in the laboratory in the absence of underground nuclear testing to support the stockpile stewardship program. And also with implications for inertial fusion energy. So the first proposal was quite a bit less laser energy was originally estimated would be needed to achieve ignition in the laboratory. And then many lasers later, here we are now, the one right before the NIF, still not quite enough. But now at the NIF, we are able to achieve finally what was originally envisioned by John Nuckolls. So this was enabled by the National Ignition Facility laser. So this laser is 192 laser beams. It's the size of 3 football fields, and it's the most energetic laser in the world. It's a 2 megajoule laser energy on target. And experiments performed here, the world's most energetic laser finally enabled the creation of these little microfusion plasmas that I mentioned previously. So all the laser energy is transported down the beam lines into a target chamber that's about 10 meters in diameter, and that's shown here. Inside of the target chamber is a 1 centimeter long target that sits right in the center. Inside of that 1 centimeter long target is a capsule about the size of a BB, 2 millimeters in diameter. And what we do here is we squeeze and compress that capsule that contains deuterium and tritium fuel from BB size down to half the size of a human hair. And that's how we get our energy density to reach these extreme conditions. So reaching the fusion, ignition, and gain in ICF experiments is very, very challenging because you have to heat and compress material to these extreme conditions. And this is a DT reaction here, creating an energetic neutron and alpha particle. You have to get material to tens of millions of degrees for this reaction, and we want to do it for enough material so that we can get significant fusion energy output. And to achieve ignition, we have to do this for a duration of time too, so a Lawson criterion. We have to reach certain density, temperature conditions, and for a certain amount of time. So because this is really difficult to do, to heat material to these conditions, what we do is heat and compress only a small fraction of the initial fusion fuel. And then we also rely on the alpha heating, so absorption of the alpha particles to get to the conditions we need. We wouldn't be able to do that just by doing heating and compressing of the fuel. So this is the initial condition pie chart here. We have a capsule, the one that I showed on the previous slide. In these experiments, the capsule is made out of diamond or high density carbon, not single crystalline diamond. It's more like a blackish graphite. And then inside of there's a deep frozen cryogenic DT ice layer, and then a DT gas core. So we're trying to heat and compress the initial DT gas and a small fraction of the DT ice into this hot plasma. So this is where we've reached minimum volume or maximum squeezing. We have a really hot extreme plasma here in the center. And the way that we heat and compress that plasma is by doing mechanical work on that material using a piston that's also made out of fuel. So that's the surrounding piston at peak compression here, which is a cooler, denser DT fuel. So what we're doing is we're imploding and doing work in a spherical piston manner on the central hot spot material. And we're doing that with a DT fuel piston. And the idea is if you can get to the right conditions of your central hot plasma, and that includes high areal densities to trap the alpha particles, then you can have enough self-heating from the alpha particles to bootstrap up the temperature, reach ignition conditions, and burn up the rest of the fuel. So once you reach ignition conditions, this sends a burn wave through the remaining cooler, denser DT fuel. So the DT fuel piston coming in is really important for doing work on the plasma, but it's also really important for tamping or confining the plasma for longer burn-up times. So as we're trying to reach ignition conditions, we have a lot of losses in the system, a lot of things that are trying to cool the plasma. That's X-ray, Bremsstrahlung X-ray losses. We have conduction losses. And also, as you implode, you reach these extreme pressures, and then the plasma wants to explode back out. That's a major loss mechanism, so the explosion back out. And so it's important to have sufficient tamping to hold the implosion together long enough so that you can burn up as much of the fusion fuel as possible. Again, so the idea here is in one experiment, a burst, we're trying to squeeze the DT fusion fuel down to the conditions where we can get enough reactions to occur and have high enough areal densities of the hotspot to trap the alpha particles from those reactions so that we can reach extreme conditions in the central hot plasma which sends a burn wave through the rest of the cooler, denser fuel. So the way that we do this at the NIF is we use something called laser indirect drive. Here's a schematic over here of the 1 centimeter long target I showed a couple of slides ago. Inside is the capsule holding the DT fuel. We have holes at the ends of this cylinder, and the laser beams come in and they hit the wall of the cylinder. The cylinder is a high Z material, in this case gold, surrounded by depleted uranium. That creates an intense X-ray radiation bath, which heats up and ablates or causes the outside of the diamond or capsule material to expand outward. And in a rocket-like effect, the outward expansion of the material creates the inward implosion of the fuel, the DT fuel piston, and the remaining ablator material. So that's how we squeeze down the fuel, is by exploding out the outside of this capsule material. And then if you can reach ignition conditions, after the self-heating, you can reach pressures that are more than 500 billion atmosphere. And then if you can reach ignition conditions, then we'll have the burn spread throughout the remainder, cooler, denser DT fuel piston. And that's what really gives you the high fusion energy output. And so one of the advances of this last experiment was to increase the amount of fuel that we're burning up by tamping the implosion better. So achieving the conditions for ignition to get to the right plasma conditions so that alpha heating can take over, that demands precise control of the design, the laser, and the target parameters. And I'll walk through those in probably too much detail in the next few slides. But first, this is a few pictures of the targets, and they're really cool because they're engineering marvels. This is a cylinder that I showed in a cartoon sense a couple of slides ago. There's quite a bit of technology in the back end of this target so that you can field a cryogenic DT ice layer. And inside of the hull ROM, we call a hull ROM the cylinder, the capsule is suspended with a very thin, what we call capsule support tent, which is only tens of nanometers thick, and that's how we get it suspended in the center of the hull ROM. Even though that's so thin, we still worry about that seeding a hydrodynamic instability. And this is a fun picture of before a shot. This is where the cylinder is sitting on the end of this arm here. And this is after the shot where we blew away or vaporized this entire piece of the arm. So one of our cool yield diagnostics is how much you bend back the arm that's holding the target. So it's actually a real thing. So this is a radiograph of looking down the end of the hull ROM before shot time. And here's the diamond ablator, or the capsule or ablator we call it. It has this higher, darker region here is where we dope the diamond with tungsten, and that's for better stability and also for preheat shield. I'll talk a little bit about that later. And then here's the frozen ice layer on the inside of the capsule, and then this is the gas core. And I don't know if you can see it from where you're sitting, but there's a tiny little shadow or fleck down at the bottom. That's a little tube, and that's actually how we get the DT into the capsule. It's quite amazing, and actually these capsules are fabricated on silicon mandrels, and that's how we get the mandrel out after fabrication. So a 2-micron diameter fill tube hole here, and so small, it's amazing what target fabrication can do. But this is also something we worry about seeding a hydrodynamic instability. So we have to have very, very tight control of what we call target quality or defects and also intentional engineering features in the target, or else you can ignite. So many design parameters need to be considered simultaneously to achieve ignition conditions, and here are some of the main ones shown here. So this is just a different cartoon of the way we're squeezing the fuel piston in hot plasma. Up here is the adiabat. We need to compress the DT ice on a low adiabat so we can get to higher compressions to reach the right areal densities to trap the alpha particles. And so that's here low adiabat and also increasing the confinement time. That has implications for how long the laser pulse duration is. We also have velocity and late time ablation pressure. We need to get the implosion to high enough velocities, 400 kilometers per second, so that we can do sufficient PDV work on the hot plasma. And we also had to keep our radiation temperature, our oven on long enough so that the capsule doesn't decompress before it's reached its minimum volume. We also worry about hydrodynamic instabilities. We worry about traditional instabilities at interfaces like Rayleigh-Taylor mixing at interfaces. And we also worry about instabilities that are seeded by things like the support tent or the fill tube, or particles of dust that fall in the capsule can also send in mixed material. So what that is that jets in your capsule material into your hot DT plasma and radiates the energy away, and then you can't reach ignition conditions. It also, for the Rayleigh-Taylor instability on the outside, it can affect the way the maximum compressibility of the DT fuel piston. And then we also worry about low mode asymmetries. So not like the high mode instability shown here, but more of the low mode asymmetries. And what that does is if you're not spherically compressing or squeezing your plasma, you can't efficiently convert the PDV work to hotspot internal energy or hotspot plasma heating. So this is an example of something that has a lot of asymmetry in the DT fuel piston, and it's kind of squeezing things asymmetrically and not getting to ignition. And to make it more fun, what's best for achieving the right implosion conditions of the capsule is usually more difficult to achieve in the way that we're doing it with the laser hull round. And I'll talk a little bit about that challenge in a slide or two. So the way that we design these experiments is using a two-step. This is a typical way to use a two-step process. We also have a lot of other types of calculations we run to assess the things that I just talked about on the previous slide. First, we start out with these integrated simulations where we model the radiation drive and the lasers coming in and propagating through this plasma that's expanding into the center of the hull room, and how the implosion is imploding and the conditions of the plasma. We benchmark these simulations against a variety of what we call tuning experiments. So first off, in non-ignition type experiments, we spend a lot of time looking at things like we radiograph the shell coming in, just the ablator coming in to see how spherical it is. We look at the shocks that are generated by steps in the laser pulse, and we look at them from different angles to make sure that that's spherically symmetric also. And we look at peak compression time, so we get a burst of X-rays out or a burst of neutrons out when we reach the maximum compression. We sort of benchmark our simulations to that. And then from that, we extract the radiation drive that we calculate, which is spatially frequency and temporally resolved. We take that and apply it to higher resolution capsule calculations. So we can only go, due to computational costs, we can't model the same type of resolution in an integrated system as we can just in a capsule-only simulation. So we take the radiation drive and apply it to capsule calculations and model things like the tent perturbation feature and how much the fill tube is jetting material in. And here's some Rayleigh-Taylor mixing here. And we also include things like the layers are rough on the capsule or the ablator, and that can also seed hydrodynamic instabilities. So we compress the DT fuel piston on lower entropy using multiple shocks that coalesce in the deuterium-tritium fuel layer. And that's achieved by defining very specific plateaus in the laser power versus time. So of course, we don't just slam the target with all the laser energy at once. We define a very specific, what we call pulse shaping or power versus time here, to generate a very specific radiation temperature profile. And this is a picture of, it's a shock plot, so it's a radial pressure gradient. And what that is essentially showing is how the shocks that are generated from these steps in the laser power are traveling through the ablator and the ice layers, and you want them to merge close here to the ice-gas interface to compress on the lowest entropy or lowest adiabat. And that helps you to reach higher aerial densities of your fuel. And we calibrate this early time or these early shocks with the shock measurements I mentioned on the previous slide. And then as the fuel is accelerated to extreme velocities, we reach peak implosion velocity or a maximum implosion velocity of 400 kilometers per second at about 1/6 of the initial radius. And this is to do sufficient work on the DT fuel. And that's really set by this part of the laser pulse, so how high you can get the rise and the maximum radiation temperature in the Hull. And at this point in time, we're worrying a lot about the instability between the ablator and the fuel interface here. And you can see here is a calculation of hydrodynamic or Rayleigh-Taylor instability on even finer scale than I mentioned before. And we're relying on models to balance the high implosion velocity, which is what we want, with the instability growth, which typically gets worse as you increase the implosion velocity, and also to calculate the pressure at the ablation front and that stabilization. And the models are largely untested in a focused physics type setting and include non-ideal plasma and Fermi degenerate strongly coupled plasmas as they're coming in. And we're sensitive to details about equation of state and conductivity here. So there's quite a big, rich area of things to still test and be relevant for ICF implosions that right now we're sort of benchmarking in a bulk sense or an integrated sense our performance to. And then at the end of the peak here, this bit latent time is important for what we call coast time or maintaining the coast time. So this is what I mentioned, you have to keep your oven hot enough as long as you can while the implosion is coming in. So now we're at about a 1/25th of the initial radius or 1/30th of the initial radius. And if you let your Hull cool off too soon, the implosion can decompress, and also it's not the most efficient way to convert energy to the hot plasma. And so now we're well into the HED regime, Fermi degenerate, strongly coupled plasma in the shell and weakly coupled in the hotspot plasma. All right, so switching gears, this is sort of, these are sort of the main parts of the laser pulse. And so switching gears a little bit, I'll walk through how we've adjusted some of the implosion parameters I spoke about a few slides ago to make progress since the start of the NIC to get to where we are now. So the best way to kind of look at, to explain how we've made progress, going all the way back to the beginning, is by trying to improve a key parameter called the hotspot energy density. So you need to get the hotspot dense enough so it traps enough alpha particles, and you want to get enough energy into the initial hot plasma so you can create enough of the fusion reactions to bootstrap up and self-heat. And so this is a plot of hotspot pressure versus hotspot energy. And here we're taking out the impact, or in what we infer, of the bootstrap heating, because that amplifies pressure and energy. So to really see how well we're assembling the plasma, we take out the impact of alpha heating in these quantities. And you can visualize where you are in this parameter space in relation to the ignition boundary, which is loosely shown by this dash region here. And so the idea is if you can get enough hotspot pressure and energy, or energy density, you cross this line and you ignite the central plasma, and then you start to get propagating burn into the rest of the cooler fuel. And these gray points here are simulations underneath the theoretical curve. So starting out in the early part of the NIC, there was, we kind of define our understanding by different design eras. Starting out early on, the attempts were made at really high gain designs with really high convergence and also using plastic ablators. And what we found was the fusion energy out was very low, but also the pressure and the hotspot energy was low. And quite a bit of work went into simulating and also measuring or validating these simulations to figure out what the issues were. And this is a simulation of the hot DT plasma in the center surrounded by the DT fuel piston. And what you can see is it's very rough looking and also very non-spherical looking. So early on, we had a lot of issues controlling the radiation drive symmetry surrounding the capsule, and so that created this low mode diamond-like shape. So the low mode symmetries I said were an issue. And then the high mode features here are from the high convergence plastic being sensitive to the hydrodynamic instabilities. And then these features here are where the tent is shooting capsule material into the hot plasma. And here's the fill tube, so a whole array of fun things. And then moving to changing the design to the next phase, which is called the high foot, is this green region here. We were able to, with the same type of hull ROM at this point, so the same type of low mode asymmetry, the same tent feature here, but a lot less high mode structure. We're able to better control the stability by increasing the ablation pressure early on. That's called the high foot, and that required giving up a little bit in the total gain that could be achieved out of the system. So not quite as high convergence, but overall higher fusion energy because we were controlling the instabilities. And then moving up to the salmon color here, things are starting to look much more spherical. The tent feature is not as big of an issue. And this is because we went to diamond ablators, or high density carbon. And they're less susceptible to the tent perturbation feature because of the higher density was really what was driving that sensitivity. And also the higher density ablators, you always want a little bit of ablator material around at the end of the day, because if you burn it all off, then all you have left is a DT fuel piston, and it's not the best for compression and stability. And so you could get the same amount of ablator mass, but a thinner ablator layer with diamond than with plastic. And so that enables us to significantly reduce the time that the laser pulse had to be on. And if you keep the laser on too long, eventually the hull ROM fills up with plasma and you can't propagate the laser beams in anymore, and you get all these low mode asymmetries. And so with the shorter laser pulse, we were able to really get better spherical symmetry. So as you can see, this is great, but we could still keep going up in pressure. But if we don't couple more energy to the hot plasma, then it will never cross the ignition boundary. And to achieve these conditions, we ended up having to go to smaller scale to get the hull ROM to work. And so we knew what we would need to do to get more energy coupled to the hot plasma was to increase the scale of the implosion. However, this design was already using the full power and energy of NIF, 480 terawatts and 1.9 megajoules of laser energy at the time. And so that was the major challenge, was how do we move right on this plot, not let the pressure fall, and do it without any more driver energy. Okay, so this is sort of redundant to what I just said. How do we move right on this plot? One point to make here is that because we're trying to balance what the hull ROM can do, together with all of these considerations about the implosion, we know that we don't have perfect predictive capability. Then we didn't know how big we could go, basically. So we set out to test 2 different implosion scales with the intent that we could optimize through experimental testing. So one of the big challenges when you increase the size of the implosion, but you can't just scale everything up bigger, you can't make the hull ROM bigger, is that you lose control of the symmetry of the radiation drive surrounding the capsule. So when you go to a bigger implosion, you need more drive to implode that extra mass. But if you don't have more laser energy to increase the size of the hull ROM, you have to do it with the same size of hull ROM. So this is essentially making the implosion bigger, but not making the initial capsule size bigger, but not the hull ROM bigger. And this is a radiation hydrodynamic simulation of the expanding wall plasma and the laser beams coming in. This is about midway through the laser peak of the pulse. And then on the right-hand side is a little cartoon of what's going on. So for the larger ablators, there's less room for the laser beams to propagate beyond the expanding ablator and beyond the expanding wall bubble in to reach the center of the hull ROM. And so what that does is that creates a drive deficit or less radiation temperature at the center of the hull ROM. And that makes a squashed or pancake type implosion. And in addition to that, it's not just the final shape that matters, it's controlling that throughout the entire 3 steps of the laser pulse. Because if you burn off more on one side in the beginning and you can achieve symmetry later, you might not have a symmetric DT shell and ablator material that surrounds your hotspot. So the shape matters, but also the rho r asymmetries matter for confinement. And so this is very difficult for our simulations to model. We can model pretty well. It's impressive almost all the way through the laser pulse, but not the end of the laser pulse. So we couldn't quite figure out how the beams were going to be clipped as this wall was coming in. And so we rely on a semi-analytical model that's benchmarked against experimental data over the last few years in these holoROMs to help us get closer in getting the symmetry right with fewer shots. So we don't have infinite shots to just sit there and test things. You really have to try to learn as much on one shot as you can and try to be as close as you can on a given shot. And in addition, the way that we got more drive to the center of the holoROM was that we let this laser beam hitting the outside of the holoROM give energy to the laser beam hitting the inside of the holoROM through a cross-beam energy transfer. And you do that by changing the relative wavelengths of the incoming beams. And that together with, that creates a density modulation that then can allow you to scatter light from one beam to another. So the initial test increased energy significantly, but suffered in pressure, and that's shown over here, this region here. It actually did still take quite a bit of time to get over to the right in hotspot energy with the larger implosions. That was for a couple of different reasons. It took a while to get the symmetry right with the smaller holoROMs. Another thing was that the initial test used capsules diamond. When we scaled up the size of the capsule, we had an unexpected surprise in target fabrication where all of a sudden there was thousands of voids throughout the diamond. So I don't know if I have a picture of it in here. Let's see. Nope, I don't have it in here, but we can do a radiograph and look at tomography, and you can actually see all these voids throughout the entire diamond shell. And so that seeded a lot of the mixing of the ablator material into the hot plasma. And it's something that you can observe by looking at the X-ray emission. We image the X-rays from the hot spot, and you could see little, what we call them meteors, and they would be little bright spots and chunks of capsule material being shot into the plasma. And so one thing we did to get to the right was we increased the size of the thickness of the DT ice layer to try to protect the hot spot from this mixing. And that did help for a little bit, but eventually we couldn't push the implosion. So that's kind of where we ended up in this bottom region. Another issue was that the coasting time or the late time oven temperature, it was harder to keep it hotter while you had the bigger capsules coming in because they take longer to implode. Then the smaller capsules implode faster, so you don't have to keep the oven as hot long enough. And so one big advance was moving up here, which this capsule is only smaller by 50 microns, which is about half the size of a human hair. And just by reducing the initial capsule size by that much allowed us to implode the capsule earlier with our given amount of laser energy, that this coast time was hot enough at the end when it was coming in. And this was all motivated by our simulations too that were benchmarked to the data. So we are getting closer here. So with the smaller scale implosion, you can't couple quite as much extra energy to the hotspot, but you were able to regain this pressure here. So the net effect was moving closer to the ignition boundary than we were with the slightly larger capsules. And this is what is referred to as a burning plasma regime. So then we knew we wanted to couple more energy at that point, but we didn't want to give up on the scale. So we wanted to stay at this scale and not go lower, or not go higher and let the pressure drop, and not go lower and let the energy be reduced. So the way that we moved further to the right on this plot is by making the holoROM even more efficient. And what that means is for the same amount of laser energy in, you get more drive out. And we wanted to reduce the coast time even further. That's how we wanted to use the extra drive. But we didn't have any more laser energy to do it. So we reduced the size of these holes at the end of the hull-rom, and that's one of the main ways that radiation is lost out of the hull-rom. So that increased the radiation potential for a given laser energy in. So for lower laser power here, you could reach the same radiation temperature here and use the extra power or energy and tack that onto the back end and extend the radiation drive and reduce the coast time. But it's not just as simple as shrinking down the holes as much as possible, because the beams have to get in and you want them to go in specific places on the wall so that you can control the time-dependent radiation drive symmetry. So when we shrunk the size of the laser entrance hole, quite a bit of work went into trying to re-optimize the implosion symmetry surrounding the capsule. So this experiment here did cross into the ignition regime, this regime here. That was a 210808 or August 2021 experiment, and that's ignition by Lawson criterion. And remember, this plot here is taking out the impact of alpha heating on these quantities on pressure and internal energy. When you put back the impact of alpha heating, the actual inferred from the experiment pressure and energy, it's off the charts here. And what that does is, because of the alpha heating and bootstrap heating, it significantly increases the fusion energy out. So once you get close to the ignition boundary where you get more alpha heating, a small change in this parameter space makes a huge change in fusion energy, going up from here to here. And the yields went up by about a factor of 8. We did a set of follow-on, what we called variability experiments, where we took this design and tried to repeat it a few more times. But those experiments at best got about half of the yield of the August 2021 experiment. And that was because this experiment used a very clean, very pristine capsule with not a lot of dust on it, not a lot of defects. And then it also had pretty good symmetry. So in addition to the symmetry I talked about, the intentional design symmetry, you can always have unintentional odd mode asymmetry. Like one example of that is where the top half of the hull-rom, those lasers deliver slightly higher or lower than the bottom half of the hull-rom, and that can create an odd mode asymmetry or a mode 1 asymmetry. And what that does is that can create a thin spot or a thick spot on one side of your DT field piston, and that shoots the hot spot out into one direction. And you can't get ignition because you can't squeeze the plasma as well as you need to. And then because the follow-on experiments, we knew this going into the experiment, but we wanted to see what would happen because we don't have a very good predictive capability for how well each different defect might impact the implosion for a different design. And so, like, here's an example here of before the experiment, we noticed a high Z flake or particle fell off of the hull-rom and landed on the capsule. But we shot it anyways, and sure enough, it produced a really bright source or meteor of emission. This is an X-ray image of the hot plasma, and it's radiating its energy away. And what that does is that just reduces the fusion yield and pulls you back away from the ignition boundary. So the idea after this, and this slide was left over from APS last year, so this is, now I'll talk about the stuff that's happened since then. So we made changes to the design to try to not be so sensitive to these things that are really hard to control, small variations in the laser, perfect targets without defects. And that's called the Higher Energy Thicker Ablator campaign. And that was enabled by more laser advancement. So we went up 8% in extra driver capability, and that allowed us to make design changes to be less sensitive to these issues. So the Higher Energy Thicker Ablator campaign, which has done 2 shots now, has used an extended laser pulse. So we got a little bit more laser energy, but it had to be at the same power because we're walking up an optics damage of the laser. So to be safe, they said you can extend the laser pulse a little bit. So at that time, the best use of extending the laser pulse, since we had already reduced the coast time quite a bit for this implosion, was to make the ablator thicker and make the implosion hang out longer at larger scale and absorb more of the radiation drive. So this ablator was increased 6 microns on 79, so also about 7.5%, and that doesn't seem like that much. And I'll talk about the other advantages of a thicker ablator in a couple of slides. Of course, this is enabled by awesome laser upgrades by the laser team. Kudos to them. And just as a shout out of things to come, eventually next year we'll be able to go to increase laser energy and go higher power up to 480 terawatts. Right now we're at 440 and 2.2 megajoules. So basically what we do is take the red pulse here and put power onto the top, and that would enable driving really thick ablators to the same implosion velocity. So you want to drive the thicker ablators but have more drive power to do that so we don't give up on implosion velocity. And this is the extended radiation drive that comes from the extended laser pulse. So as every time you make a design change, you have to think about the symmetry. So extending the laser pulse just by a few hundred picoseconds was, again, more difficult for symmetry. The longer laser pulse had more plasma filling, and you have to counter that late time plasma filling with early time drive so you can swing just the right way during the peak of the laser pulse. And so what we did was we dialed up the amount of energy that these beams gave to these beams and readjusted the symmetry, which is the different laser powers that are defined differently on these beams versus these beams throughout the entire laser pulse. And I have a picture of that a little bit later in the talk. So the thicker ablators are really cool because they help us increase this hotspot pressure and energy, the energy density, so that we can be further over the ignition boundary so that when things happen like mode 1 or mixing, that you fall back but you still get to high yields or ignition. And then eventually to get even further over is the goal, so you're not as sensitive to these issues. The thicker ablators also increase the confinement, so you have more tamping and you can burn out more of the fusion fuel. So if you have the same perturbations as before and you don't get pulled back to the ignition boundary, you can burn more. You're more into the burn propagation regime. And the thicker ablators are also better for the hydrodynamic stability. So at peak implosion velocity, you have a more dense ablator compared to the DT fuel, and the higher density at that interface makes a much more stable Atwood number and less mixing between the ablator material and the fuel material. And here's a picture of just like what that mixing might look like between the ablator and the fuel. So this is a plot showing that with the extra margin from the design change, we can tolerate more perturbations. And so this is a plot of yield versus a perturbation here where in the simulations I dialed up the amount of roughness at all the interfaces by 1, 2, 3, 4, and 5 times what we think it actually is. And that makes something that looks really mixy here. This is a DT fuel piston in the hotspot and reduces the hotspot volume, etc. And as I do that for the new design in red versus the old design in black, there's a lot more margin to still achieving high yields at a given amount of increased perturbation. Okay, so moving on to tests of this new design. We had 2 tests so far. The first test in 22 was in September of 2022. And well, whenever you make a change to the design, you also have to make sure that the backscatter team is okay with that, and Pierre's not here. But whenever you change the conditions, the plasma conditions in the hull room and the lasers entering it, there's a potential to create a situation where the laser plasma interactions or the lasers coming in interacting with the high Z expanding wall material can create stimulated Brillouin scattering that scatters light directly back into the optics, and that damages the laser system. And so whenever you do that, you have to walk up. What we call walk up is don't dial it up to where you want to go to start out, but do it like part way, and then we'll see what the backscatter looks like, and then you can go further. So for this first experiment, as I said, we had to dial up the amount of energy being given from certain beams to other beams. but we could only go part of the way there. And so what we ended up with something that looked a little bit squashed, kind of like a pancake. So this is the first test here, kind of squashed compared to the 210808. But the good news was it's sort of proof of principle that as you're dialing up these perturbations, we still achieved high yields comparable to the 210808, even though that this was present and we saw that. So we simulated, we do pre-shots and post-shots. So after this experiment, we simulated the conditions, and then in the simulations took off that or improved that symmetry, and we expected that we would get a yield increase by improving the symmetry. So that motivated a test to fix the symmetry, that there was a there there, that it would make a big difference. And so to fix the shape, we dialed up a little bit the amount of energy being transferred from the outer to the inner beams, and then rejiggered a little bit this inner beam power versus time to outer beam power versus time. So here's a plot of what I was talking about earlier. Here's power per beam as a function of time. Here's the steps here. These orange curves are the powers that are given to the beams that hit this part of the hull realm. And this is the power given to the beams hitting the inside part of the hull realm. And that's so that we have symmetry during the entire time history. Otherwise, you get the rollbar asymmetries of the fuel and the ablator. So in addition to dialing up the amount of energy given from one beam to another by adjusting a little bit the relative wavelengths, also these powers were changed just a little bit. And this looks like very small changes, but these are actually the types of changes that are important to make for symmetry. So those adjustments to the symmetry were the only change between the first test and the second test. And as expected, the yield increased by about a factor of a little bit more than 2.5 times, going from this experiment up to this experiment here. And also we observed that the hotspot was indeed symmetric. And so this led to now meeting all the goals, or all the definitions for ignition. So not just the Lawson definition, like this guy here, but also the National Academy of Sciences definition of ignition is when this fusion energy is more than the energy of the laser into the target. And this is what we refer to as target gain. So we got more fusion energy out than the laser energy put into the target. Here's a plot of how this looks in Lawson criterion space. So now this experiment, this label got copied and pasted. That 210808 or August 2021 is over here. And this is a new experiment over here further into the ignition boundary. And here's pressure times confinement time and ion temperature. And after you cross this boundary, it's the Lawson criterion for ignition, and here's a new experiment over here. So there's also several other published metrics for ignition that these shots all now pass. And this is something that's determined using measured or inferred quantities for the pressure and confinement time and ion temperature. Switching gears a little bit now. So this shot was important or motivated a lot of other approaches for achieving fusion, because it's a proof of principle experiment that you can, in a controlled laboratory setting, you can get more fusion energy out than was used to drive the experiment. Of course, there's many different approaches right now and lots of different companies within an approach. And so but there's still a long way to go there's different considerations for each different approach. Each one has its own challenges. We share a lot of the same diagnostics, so things that are used in ICF could be used for other IFE type plants. However, there's still quite a long way to go, and in particular for ICF, we need higher gain designs and better engineering developments, cheaper targets, and more efficient lasers. And this is a little bit more of a complete list talking about those things. So this is a slide on how does a design, all the stuff I just talked about, become even more challenging for an IFE type situation. We need more coupling of driver energy into hull realm temperature to make that step more efficient. We can do this with higher efficiency hull realms. We can do this with direct drive, which has other challenges, so directly hitting the capsule with the lasers, and novel geometries. Also, double frequency. These are all ideas. We need higher gain designs so that for a given radiation temperature, you get more fusion energy out. You can burn up more of the fusion fuel. A clear way to do that is better confinement. So right now we've reached ignition conditions of the hotspot, and we're trying to also have enough confinement so we can burn up more of the fuel surrounding the hotspot. We need robust target designs that are suitable for high rep rate and harsh conditions. We need cost-effective design, so we're looking at alternative target materials, amorphous ablators, B4C ablators, lead holograms, that sort of thing. And then we need to rethink the way that we set up the fuel configuration. So instead of having a cryogenically cooled ice layer, which takes a long time, there's ideas to use a wetted, what they call wetted foam, so a very, very low density foam layer, which has liquid DT in it. And then think of alternate methods for supporting the capsule in the center. And then there's also other types of ICF designs which look very different from this. One of them is called fast ignition, where you assemble the fuel very asymmetrically and much slower. And then you ignite the central plasma with something like a proton or electron beam. And so that development of those igniter type beams is something that people are looking at. Of course, there's many other ideas out there. So what's next at NIF and what we're doing at the basic research facility at NIF is to continue studying the parameter space around these igniting and gain experiments and trying to push to higher yields by increasing the confinement and the efficiencies. So understanding use, we're measuring more of the plasma conditions surrounding this igniting experiments and also perturbing the experiments to see what we're sensitive to. We're also using these implosions as a bright neutron source for stockpile stewardship applications. And we're pushing to even higher yields, or that's the intent, is by increasing the laser energy even more, as I discussed, going thicker ablators. We're trying to increase the efficiency of the hologram. We're trying to compress the DT fuel piston down better by seeing if we can go back to lower adiabat or lower entropy, and also trying to hydroscale up the implosion. Now that we're getting better at the hologram and the capsule physics, can we go back to the slightly larger scale and get more out that way? So it's a very exciting research time, and with that, I'll take any questions if there's time left.
Are there any plans to build a next generation of NIF?
So currently we're talking about a NIF power and energy upgrade. So right now the 2.2 megajoules is something they can already do by optimizing the system that we already have. And then in the next 5-ish years, we can implement certain upgrades without building a whole new facility to go up to 3 megajoules of laser energy. So that's what we're currently talking about now, is an upgrade. That's a great question. I have a nice diagram because people always like to ask this question, understandably. So only a small fraction of the laser energy in this configuration is coupled to the hologram and also the implosion. So let's see if I can get so here's like the laser energy into the hologram, and then we make the X-ray radiation bath. We have some scattered light back out from laser plasma interaction, some amount of hot electron generation. And then we have some amount of heating going into this low density gas inside of the hologram. And then we have a lot of the energy goes towards heating of the hologram walls or hologram wall losses. And then and then losses out of the laser entrance hole. And so only about 10 to 20% of the initial laser energy is actually coupled to the implosion, to the capsule. And that's used to implode the entire thing. So if you're looking at coupling to the actual hot plasma in the center, it's even lower than that. So there's clear advantages to doing things like trying to make the Hallraum a different shape so you have less losses, Hallraum wall losses. That's challenging for symmetry, so that's something that we're working through right now. But more efficient ways to couple the energy to the capsule implosion also.
Since that's fairly novel, the application of Hallraum, is there any technology to support that, or?
Yeah, actually, so I don't have a picture in this talk, but it's just a question about symmetry and if you can like change the shape of the Hallraum and still control how symmetric the drive is. So right now, and actually we'll be doing some more tests in May, we're currently testing in the symmetry tuning experiments, taking the wall here and cutting it off and sort of reducing the size of the wall so it looks more like the shape of a rugby or like two triangles put together. But it's been very challenging for getting the laser beams past those walls, and also they can interact more and have more laser plasma interactions with the wall because they have a similar angle of incidence. But it is looking promising, and so we've been able to control the symmetry with this crossbeam energy transfer in a way that looks like it might work. So and it does have much higher efficiency. We measure that. So the key is getting the symmetry. We also tested things like pockets on the outside to keep the wall back, so kind of like the opposite idea. And that did work, but it reduces the drive a little bit. So it's like if you squeeze it down enough, and then you need a little bit more symmetry. And we're looking at further reducing these holes also and trying to get that symmetry. So it's all like we have a few different ways we're trying to improve the efficiency, and all of them are trying to also get symmetry to work right now.
Tell us a little bit about the transverse aspect of running the experiment. Like, do you get ongoing contamination on the view parts, or do you get also floating flash lamps and so on?
Yeah, so after the first high yield experiments, I think some of the lights went out in the building, so that was cool. So the order of operations kind of changed, and since this is big science, the physicists don't actually go into the lab and adjust things. You have an entire facility that's run by technicians and engineers. And so, but we do worry about things like debris falling on the optics. So like the gold target that you'd completely vaporize, that debris goes somewhere. We have debris shields, and those need to be replaced. And so it is kind of like what you're thinking about, but not as fun as like getting in there and wiping it off myself.
I was wondering about the diagnostics that you use. Is anything that you can actually image happening after the Hallraum comes up and the updates are activated, or is there any way to actually see what's going on there?
So we have a lot of diagnostics. It's actually, and there's tons of people working on this. It's quite amazing. So in addition to the diagnostics I talked about earlier of like, you can actually measure the shocks coming in as they're coming in, step 1, 2, and 3, in different directions. And you can measure the shell as it's coming in and the shape of it. And then there's so many things also that you can measure about the hot spot plasma when it's squeezed down to its smallest size. So we have things like neutron time of flight detectors to get ion temperature. You can look at what we call the hot spot velocity, how much it's squirting out in one direction because we have it along multiple lines of sight. And then the yield from that, we can actually look at the fuel uniformity from a DT yield map. So the primary neutrons that are generated in these fusion reactions, they scatter to lower energy when they go through the dense fuel. And so if you look in all around the chamber and you see more yield here versus less yield here, you know that the fuel piston that surrounds your hotspot, what that shape looks like. And these are the maps here. And then we also have, you can image the neutrons that come out of the hot plasma and the neutrons that are downscattered in the surrounding plasma. and you can correlate those two images and look at the shape of the shell. So like in some, this is real data. We saw like there's a big hole on one side. That's not good. And like here we have the dense, DT is dense at the poles. That's due to a controllable asymmetry. And here's like a little picture of our hot plasma as it's measured with 3D neutrons and neutron imaging of the primary neutrons from the reactions from 3 different lines of sight. And then we have our X-ray images from different lines of sight, so we can look at things like, does the X-ray emission from the hot plasma correlate with the neutron emission? Or is there like a bunch of X-ray emission and there's no neutrons there? Then that means it's mixing, it's cooling the plasma, radiating energy away. We have spectroscopy too, so we have imaging, but we also can look at the line emission. And because we dope the capsules with tungsten, you can actually get line emission and get like the temperature of the plasma coming in. We have, we measure the burn duration. So we measure the number of neutrons as a function of time coming out of the implosion. We measure what we call bang time, is when you get the most neutrons out at a given time. So this is just some of it. There's a lot more of it. There's tons of diagnostics.
Yeah. So right, so you mentioned that there's Fermi general and primary coupled plasmas, a bit unusual. Like you said, it was burned phenomenality and it goes into a diamond. Are there experiments on plasmas in that regime that are either done elsewhere or could be done elsewhere than us?
Yes. Let me go back to. Yeah, so I don't have a nice picture of it in this talk, but in another talk that I give to some of the universities that want to measure these things, you can track different parts of the implosion and see where they go in pressure and density space and the trajectory they take. There's focused experiments that can look at different regimes. There's like, so there's planar geometry type equation of state measurements. We also have an experiment where we take the capsule, and instead of having a hollow capsule with DT fuel inside, we have a solid ball of a material. And then we look at the shocks coming in and radiograph the shocks coming in and can use that to determine an equation of state at very high pressures, gigabar type pressures. So there's a lot of focused physics experiments that try to get at different aspects of these physics regimes. And we had, excuse me, we had one of these spherically convergent shocks accessing the states of a white dwarf exterior also, which is relevant also for the ICF experiments. So there are things that can be done and are starting to be done more routinely, but there's so many parts of parameter space that should be benchmarked for these experiments.